So we want to talk about classifying matter today. We've learned what matter is, right? Who can give me a definition of matter?
Anything that has mass and takes up space.
It has mass and it takes up space. So like you said, matter takes up space, has mass, right? We define that as matter. But that encompasses almost everything, right? So we need some way to classify that even more. And so we're going to break matter down in a couple other categories now. So let's talk about classifying matter. And the first type of matter that we want to mention is what we call a pure substance. All right, so a pure substance is a substance whose properties are the same throughout. Properties are the same throughout. All right, so we'll talk about some examples of that in just a second. So that's one category. In the second category, we're just going to break matter up into two categories here, two classifications. The other classification is, instead of a pure substance, it can be a mixture. And so a mixture is a combination of two or more pure substances. So that's our top level classifications of matter. In fact, let me do this. Matter. So we're going to break matter down into those two. Pure substance, mixture. And so an example here of a pure substance would be salt, for example. But an example of a mixture would be salt and pepper in the same shaker. All right? So the properties are the same throughout. If you pick through the salt, right, it's going to look like the same substance all throughout the shaker. But if you had salt and pepper mixed together, you'd see the little pepper flakes in there compared to the salt crystals. So how do we, sometimes this is not as obvious as like salt and pepper mixed together, right? We would see that, we would obviously say that was a mixture. How can we kind of, from a chemist standpoint, determine the difference between the two? And this is the statement we want to make with that. If a sample of a substance can be separated into different substances by a simple physical process, it is a mixture. So salt and pepper in the same canister, right, in the same shaker, it's definitely a simple physical process. I might have to get my tweezers out, right, but I could one by one separate all of the pepper out of the salt and separate the two, right? So a simple physical process allowed me to separate that. But what about a substance such as salt water? Salt water Looks like it's the same thing all throughout. It seems like it would be a substance whose properties are the same throughout. But salt water is actually a mixture. And the reason we know that is because we can perform a simple physical process and separate out the salt and the water. And how would we do that? We would boil it, right? So if I were to boil, so what I should do is I should just give you guys both, like put your name at the top. If one of you says something, just put both of your names and then I would never be wrong, right? Because the other one's definitely going to talk in class, right? Can I count on you guys to always do that? And then I just always put you together? You're not going to make it easier on me. All right. So if I boil it, if I boil salt water and I collect, the condensation at the top of the container there, I'm getting pure water again. And after all the water boiled out, the salt would be left in the bottom, right? So I could separate it through a simple physical process. And so salt water is actually a mixture. So we could add that here as an example. Does that make sense to everybody? Any questions about that? All right, so we've got these top two categories for matter. Let's talk about mixtures. Let's actually break mixtures down into two. So we're going to call this classifications, right? Two classifications of matter. All right. Now let's talk about a couple of categories of mixtures. And I guess, really we're classifying mixtures too. So you could say classifications of mixtures. But I just want you to see the top level is pure substance and a mixture. Those are the top two classifications. And then below that, you've got these subcategories. So classifying mixtures. Mixtures can be broken down into homogeneous mixtures and did I start recording? Yes, I did. Okay. Homogeneous mixtures, and that is for a homogeneous mixture, the composition is the same throughout your sample. So for example, milk would be a homogeneous mixture. Salt water that we just talked about would be a homogeneous mixture, right? No matter where you take a sample of that mixture, it looks the same, it has the same makeup, it's thoroughly mixed together. Versus a heterogeneous mixture. And with a heterogeneous mixture, the composition is different depending on where you take a sample. So an example of that might be Italian dressing. And I meant to figure out what the little things were in Italian dressing before this class because I didn't know in the last class either. Does anybody know what the little dots are in the Italian dressing? So whatever it is, you may have more dots in one sample than you would the other, right? Or here's maybe a more meaningful example: milk and cereal. Right? That's a mixture, and it's clearly a heterogeneous mixture because I might grab a spoonful of my Lucky Charms in one bite, and to my dismay and my great disappointment, there would be no marshmallows in it, right? That would be terrible. And then you could do actually the way I like to eat Lucky Charms, eat all the whole grain things first, and you'd be left with nothing but marshmallows, and then you could have a spoonful of nothing but marshmallows. The sample's not the same, the makeup's not the same, throughout. It changes, right? So that's what a heterogeneous mixture is. So homo meaning the same, Homogeneous mixture, the composition is the same throughout. Hetero meaning different. The composition is not it's not the same all throughout. It's different depending on where you take the sample. Everybody clear on that? Does that make sense? So those are our two categories of mixtures, right? Homogeneous, or homogeneous, and heterogeneous. All right. And so when you read through this in the book, you're going to see that Dr. Weil describes how air is a homogeneous mixture. It's the same wherever you take the sample of the air, the makeup of air is perfectly balanced. And he talks about how needful that it is that it be perfectly balanced. That if it even varied slightly, it wouldn't support life, right? So it made me think about a passage in Acts 17, 24 and 25 that says this: God made the world and everything in it, and he doesn't need anything from us. And I'm leaving out a portion of it, and I don't have it right in front of me. This is just what I've written down here. But he made everything in the world. He doesn't need anything from us, but he gives to all life, breath, and all things. And I was like, that's an example of what God has done for us, right? And this perfect mixture of our atmosphere is something that's perfectly balanced. It's just the right combination, and it's consistent throughout, so that it can support life here. So that's a gift of God. I mean, that's one of the things that maybe we don't think about every day that we experience, right? But we ought to give thanks for that. Every time I take a breath, it works, right? Every time I take a breath, it's something that's actually going to benefit me instead of hurt me. And that's a gift from God. This passage here says in Acts. Paul was talking to, if you're familiar with Acts 17, he was talking to the men of Athens, the Athenians there, who had all these different gods, and he was going through there and he found this one statue that was to the unknown God. And he was like, that unknown God, the one that you don't know, that's the God that I'm declaring to you, because he's not like any of these other gods that you've built temples for. He's like, you can't build a temple to contain this God, right? This God's outside of all that. In fact, we're all inside of him. He supplies for all of us. And so he used as an example of that, he gives breath to every one of us. So that's actually a convicting thought if we consider the fact that every time we take a breath, if we're not thankful to God for what he's provided for us, we're really robbing God of that which he's graciously provided, right? We ought to give him thanks and praise for that which he's given. And that's what Paul was calling the Athenians too. But anyway, so that air is a homogeneous mixture, and it's perfectly balanced to be able to sustain life. So pretty cool. Let's look at, give you another definition. By the way, this is almost all definitions today. We're going to do one example at the end, but we're mostly just kind of defining some things. So we've classified mixtures, and before we move on to a couple of classifications of pure substances, we need to talk about a law that I want you guys to be familiar with and remember. It's the law of mass conservation. And that law says, in any chemical or physical process, the total mass of everything that's involved in that process must remain the same. So the point being, if you have a chemical reaction, if you have some kind of physical process, whatever you started with must be the same as what you end up with. The mass must be the same. And I actually left off that word right there. That was critical. The total mass. Sorry about that. The total mass of everything involved must remain the same. So the mass at the beginning must equal the mass at the end. So there's an experiment in the book that we're not going to do, experiment 2.2, where you basically, you add some, you have a certain amount of milk and a certain amount of vinegar, take the mass of each of those, and then you mix them together, and this chemical reaction takes place, and it basically makes the milk curdle. So now you've got these chunks inside your milk. Yeah, I thought it was kind of a disgusting experiment, right? So why would I want to do that? But because this chemical reaction is taking place, and now you've got this solid stuff in there where you had liquids only before, you might be tempted to think that it's going to weigh less, or the mass is going to be less, or maybe the mass is going to be more. But you see that the mass stays the same. Because when we did the reaction, everything was contained in the same vessel, and so you can easily see that the mass that you started with, as you combine the two together, was the same mass that you ended with, right? So that's what the law of mass conservation teaches us. Now, sometimes it can be hard to prove that. For example, you burn a piece of wood, right? And so you take the mass of the wood before you burn the wood, and if you can capture everything, right, you capture all of the carbon dioxide that's produced, and you gather up all the ashes after you burn the wood, and you captured all the water vapor, because water vapor is something that's produced as you burn wood. If you were to capture all that and you would look at the mass afterwards would be greater than the mass of just the wood before. Can anybody tell me why?
Would that be because you got some would that be because you got other particles in the air as well?
Exactly. So, and specifically because of oxygen, because we got to have oxygen in order to burn the wood, right? So what happens is that you've got to take the mass of the oxygen into account. So if you calculated the mass of the oxygen along with the mass of the wood, then that total mass would equal the total mass afterwards. But yeah, that's exactly right. Good call. All right. So does that make sense to everybody? Any questions about that? Yes.
Is there any way that a physical process could for sure change the mass, or is that just like a given?
No, it's a law. It's a law that all the stuff that we're doing in here is going to abide by. That the mass you start with has got to be the mass that you end with. Okay. So yeah, good question. It's something that we're gonna. The rest of the year we're going to be doing calculations based on the fact that this is true. Whatever you started with, you have the mass of that you have to end with, right? So good question though. All right, it is Isabella, not Isabel, right?
Yes.
Yeah, with a name. Okay. All right, so let's go on to the classifications of a pure substance. And we're going to talk about, again, something that I know in your scientific career that you're already familiar with, but we have to define these things before we can jump into deeper study. An element. An element is a substance that can't be chemically broken down. Into simpler substances. And then if we're talking about elements, we'll also talk about compounds. And a compound, kind of like
Is oxygen a compound?
No, oxygen would be an element.
Water.
Huh?
Water.
Water would be a compound, right? So water is comprised of hydrogen and oxygen, right? And so an element is the simple substance, right? All those things on the periodic chart that I think maybe at the end of this chapter we're going to talk about the periodic table. But a compound is a pure substance composed of two or more elements. So what I was trying to do was, that's a very similar, what I was trying to bring to your attention is that's a very similar definition of the definition we had of a mixture. A mixture was comprised of two or more pure substances. A compound is comprised of two or more elements. So the element is the simpler substance that compounds are made up of, just like pure substance is the simpler substances that mixtures are made up of. So yeah, an example here would, like I said, oxygen would be the element. Water, which everybody knows is H2O, two hydrogen atoms and one oxygen atom, would be the compound there. All right? And so pure substances can be classified into these two things. So that's the two categories for pure substances: elements and compounds. All right. And so what I want you to remember here, and this is, let me put mixture here, is that if I were to ask you what are the 4 categories for matter, 4 categories of matter. That's what I'm looking for. Elements, compounds, homogeneous mixtures, heterogeneous mixtures. And so it's interesting, let's talk about zinc sulfide for just a second. So zinc would be an instrument. Zinc would be an example of an element, whereas zinc sulfide would be an example of a compound made up of 2 elements, zinc and sulfide meaning sulfur, right? So let's just think about a conclusion that we can draw based on what we just learned about the law of mass conservation, all right? So let's say we have 100 grams of zinc sulfide. All right? And if I told you that we chemically broke that down, and when we broke it down chemically, we had 67.1 grams of zinc. Could you tell me how much sulfur we had? How would you do it, Cruz?
You would subtract 67.1 grams from 100. Right?
Exactly, yep. So 100 grams minus 67.1, and we would come up with 32.9 grams of sulfur, right? That's based on the law of mass conservation. Whatever mass we started with, we have to end with that mass. So if we had 67.1 grams of zinc at the end, we would have to have 32.9 grams of sulfur. Something interesting to note too is that both the elements and then the compound that's formed from the elements, they may have completely different properties. So zinc, for example, is a hard substance, but it's malleable, so you can like mash it, shape it into a different form. Sulfur is a powder, but then when you combine the two together, you form a compound with zinc sulfide that's really brittle. So it's not like really either of the two that you combine together to get that. So the properties can be totally different between the pure substances, between the elements that make up the compound and the elements themselves. Any questions about any of that? Everybody saw the little star here, right? Make sure you know what the 4 categories of matter are. Okay, let's talk about the law of definite proportions. All right, the law of definite proportions says this. Law of definite proportions. A given compound will always have the same proportion of elements by mass. A given compound will always have the same Proportion of elements by mass. So, for example, water, H2O, right? With H2O, it's always a 1:8 proportion. So, you have 1 gram of hydrogen. You'd have 8 grams of water. Hydrogen peroxide, on the other hand, which is also comprised of hydrogen and oxygen, has a 1:16 proportion. So for every 1 gram of hydrogen, you have 16 grams. That's not supposed to say water, I'm sorry about that. That's supposed to say oxygen. I can't believe nobody caught me on that. Who's sitting in this seat? What's wrong with you? That's the spot, huh? Oxygen. All right. 16 grams of oxygen, 1:16 proportion. And so what this means is that if I have water and I know instead of 1 gram of water that I actually have instead of 1 gram of hydrogen, I know that I have 4 grams of hydrogen. How many grams of oxygen do I have then? If it's water. How much? 32? Is that what you said? Yep, that's right. That's exactly right. Because it's always a 1:8 proportion, right? And so if I had 4 grams, if I multiplied this by 4 and had 4 grams of hydrogen, then I'd multiply this by 4 and have 32 grams of oxygen, right? That would keep my 1:8 ratio. Any questions about that? So we're going to do an experiment next week where we're going to see that that these will have unique properties. And we're going to use hydrogen peroxide as an example of that. How there are unique properties to the compound and there are unique properties to the individual elements. By the way, that's lab 2.3, and I can't remember if I've already said that in here, but make sure that's part of your reading this week. Make sure you read through the full lab, so that we'll kind of be ahead of the game when we do the lab next week. You already know what to expect, okay? All right, so that's the law of definite proportions. So let's do an example. On page 48, example 2.1. And example 2.1 says that a chemist uses 32.0 grams of carbon and 32.0 grams of oxygen. All right, and she combines these two together and forms an unknown gas. So this plus this makes an unknown gas. Unknown gas, and it's 44, is that what it is? 44.0 grams of this gas. Okay? And there's some leftover carbon. How much leftover carbon do we have? Can we figure that out? What does the law of mass conservation tell us? Whatever mass we start with, the total mass of everything that we start with, if we have a chemical reaction, the total mass at the end has to equal the same, right? So we started with 32 plus 32, which is 64 total grams, right? That was the mass to start with. We got a gas that's 44 grams, so we can figure out how much carbon we've got by saying 64 grams minus 44 grams equals, I should have put a 0 on both of those, 20 grams of leftover carbon, okay? Does that make sense to everybody? How we got that? How we were able to calculate that? So we can figure out how many leftover carbon that we had. So since that's the case, well, let's see what the full question is. So we had some leftover carbon. She made 44 grams of this unknown gas. She would like to make, needs 110.0 grams of gas. That's how much she wants to make, okay? And so the question is, how much carbon and oxygen should she use to make 110 grams of this gas without any leftovers? All right, that's the question. So what we kind of need to do is we need to figure out the recipe for this gas, is in essence what we're trying to figure out, based on our first, the amount of carbon and oxygen that we needed to start with. She doesn't want to have any leftover carbon or oxygen, right? And so what we need to figure out is, we know we had just enough oxygen to make this gas, but we had too much carbon, right? So how much carbon did we actually need? Well, we know we had 20 grams of leftover carbon, so we needed 32 grams of carbon minus 20 grams, because that was what was left over, right? So we needed 12 grams of carbon to make 44 grams without any leftover carbon. Does everybody see that? Right? And so our recipe then for this gas that we made, grams of carbon plus 12 grams of carbon plus 32 grams of oxygen. That was actually our recipe that produced 44 grams of gas. Right? And so if you think about this like a recipe, it's kind of like, you know, I've got a recipe for making 6 cupcakes, right? But 18 people are coming. What am I going to do? My recipe only is good for 6. Come on, somebody help me out here.
You multiply by 3.
I multiply by 3, right? We do that all the time. That's simple for us, right? That makes perfect sense. Now, you thought multiply by 3 because I told you 18 people were coming, so what you did in your head is you thought, well, 18 divided by 6, which is how many the first recipe makes, equals 3, right? So I need to multiply this recipe by 3 in order to get that, all right? So you took the amount that we needed and you divided the amount that the recipe was for. Well, the amount that we need here is 110.0 grams, right? That's what she wants to make. But the recipe that we have only makes 44.0 grams, right? And so when we divide that, that's 2.5. We came up with a nice even number with our cupcakes, but this one's a decimal number. 2.5 is what our multiplication factor is, okay? And so to make exactly 110 grams without anything left over, then we need to multiply both of these ingredients by that factor, right? So in order to make 110 grams, we need to take 12 grams of carbon times 2.5. And what is that, 30? And then 32 grams of oxygen times 2.5. And that's what? 64 plus 16, 80? Am I right? Is that what our answer is? Yep, 30. So this is actually what we need to make 110 grams with no leftovers. Does that make sense to everybody? Now you could have done it. I had a student in the last class that as soon as they figured out what the correct recipe was, they figured out what the ratio was. And so they used this, they looked at this and they were like, oh, okay, that's a 3-to-8 ratio. And so they used the ratio in their head to figure out that's what would be needed for that. However you want to do it is fine with me, but this method, works. At the end of the day, you've got to figure out what that factor is that you're multiplying it by. And that way you know what to multiply the original amount by to get what you're trying to end up with. All right, so let's, the other example here, kind of continuing with the same problem. It says the same chemist does a different experiment where she reacts 18 grams of carbon. So she's going to use the same elements. All right, this time she's got 18 grams of carbon. And she combines it with 30 grams of oxygen. To produce 42 grams of a gas. And plus some leftover oxygen. And so the question is, did she make the same gas as she did before? Now, how are we going to figure that out? Just before we actually crunch the numbers, how are we going to figure out if it's the same gas? We know that the gas is made up of the same elements, right? Both gases have carbon and oxygen in it. And so the law of definite proportions tells me that the mass of the elements in the compound for a given compound, such as water, the ratio of the masses is going to be the same, right? No matter how much you have. It'll break down to the same ratio. So like we said with water, it's always 1 part hydrogen, 8 parts oxygen, right? And so we have a ratio here. If we have 12 grams of carbon for this gas, we'll always have 32 grams of oxygen, right? So that whatever that ratio is, and like the student in the other class pointed out, that's a ratio of 3-to-8, because if you divide both of these by 4, right, the simplest number that you can break it down to is 3-to-8. So this is a ratio of 3-to-8. So we're basically trying to determine whether or not this gas has that same ratio, right? So the first thing we got to do is we got to figure out the exact recipe for this gas so that we don't have any left over, right? And so if there was leftover oxygen here, what's 18 plus 30?
48.
48 grams, right? We made 42 grams of gas. So how much leftover oxygen did we have? 6.0 grams, right? So that was, this right here is 6.0 grams. That's the amount of leftover oxygen. So then if we subtract this 6 grams here from the 30 grams of oxygen we had there, then our actual recipe is 18 grams of carbon plus 30 minus 6 is 24 grams of oxygen. That gives us 42 grams of gas. Does everybody see that? See how I got that? All right, so this is our recipe for making this gas. This is our recipe for making the other gas. Are they the same? And so the way we figure that out is we've got to figure out the ratio between carbon and oxygen, right? And so we can do that just by dividing the grams of carbon by the grams of oxygen. So in this, I mean, there's a couple of ways to look at it. Like here, we broke this down and said it was a 3-to-8 ratio. I could divide both of these numbers by 6, right? And I could just see from that it's a 3-to-4 ratio. That alone tells me that it's not the same gas, right? But I'm going to show you how they did it in the book. It's the same idea. You're figuring out the ratio, and if the ratios aren't equal, then it's not the same gas. So we had 12 grams of carbon for our old recipe, divided by 32.0 grams of oxygen. And so that ratio turned out to be what? It's 12 divided by 32. That ratio was 0.375. All right? So we got to see, does that ratio match the ratio over here? We already know it's not. We figured that out, but let's punch it in anyway. 18 grams divided by 24 grams equals, should be 0.75, right? Yep. 0.75. So because this number here doesn't match that number there, they are not the same gas. The recipe's different, right? Does that make sense to everybody? I mean, clearly if I was making muffins, and I can't even think of a good example. I was making chocolate banana muffins, right? And I put the chocolate in the name of my muffins first because I prefer more chocolate than banana, right? So I make these wonderful chocolate banana muffins that are mostly just taste like straight chocolate. By the way, if you ever want to bribe your teacher, I love dark chocolate, right? So, not that that would ever help your grade at all, I'm just saying. So they taste like chocolate, you know, with this hint of banana in it. So it's like, you know, for every 4 bars of chocolate, you know, 1 banana. But then some crazy person comes along and says, we're going to do 3 bananas to 1 bar of chocolate. You don't have chocolate banana muffins anymore, right? You got banana chocolate muffins. There's a difference. Okay? So it's not the same muffin, just like this is not the same gas because the ratio's changed. That makes sense, right? All right, cool. Well, that's actually as far as we were supposed to get today, but before you get excited, I went over one more thing. I went over something in next week's lecture for the last class because we have a lab next week. And I don't want us to run long, so let me see what time it is. So we still have like almost 30 minutes. So this will take just about 5 to 10. So let's go over this one concept from your reading assignment next week. But that way we'll get it out of the way and we'll have less to do in class next week and we'll have more time for our lab. So let's talk about Dalton's atomic theory. This was developed in the early 1800s. And by the way, on the previous statements we had, those were laws, right? We had the law of mass conservation. We had the law of definite proportion. So that means we have enough data, right? We've tested that enough that we say we're going to make that a law. Whereas theory, it sounds like a good idea, and you know, as far as we can tell, you know, maybe things tend to seem that way, but we haven't reached a point where we feel like that we've scientifically proven that, right? So a theory is something that someone proposes, and so Dalton's atomic theory basically consisted of 4 propositions. And like I said, this was in the early 1800s. So given that which they understood at the time, it's actually pretty impressive that he came up with this. But there were basically 4 propositions, and I want you to know what these are. All matter is made up of atoms. And these atoms, he said, are indestructible and indivisible. So I'll go ahead and tell you it was a good thought. He was close, but he wasn't quite right on that first one. Number 2, he proposed that all atoms of a given element are identical in all their properties. Again, something we know now is not quite accurate. Number 3. Now this one's pretty solid. Compounds. He said compounds are formed when you combine 2 or more. Why did I spell more with 2 R's? I don't know. two more different kinds of atoms. It's a pretty good statement. And then number 4, he said a chemical reaction is actually just a rearrangement. That looks like 2 R's. A rearrangement of the atoms that exist in the substances which are reacting. And kind of like with number 3, I would agree with that. So I'll let you finish writing that down and we'll talk about that in a moment. Stomach is not happy. All right, so just to talk a little bit about this, number 1, again, this is a theory, and we understand now that some of the statements are a little bit off, but it was pretty good, like I said, especially for early 1800s, given what they knew then. Pretty amazing that he came up with this. So, number 1, this part of number 1 agrees with the law of mass conservation, right? He said you couldn't destroy this matter. Matter is made up of these atoms, indestructible particles, and so that goes along with the idea that whatever mass we start with, we have to end with that mass. You can't obliterate it and it not be there, right? The mass has to stay the same. The part that we have more of an issue with is this part right here. He said they were indivisible, and even in probably physical science, and probably before that, you guys have all learned that atoms are actually comprised of subatomic particles that we call, what are the 3 subatomic particles in an atom? There's a nucleus and then something that revolves around the nucleus, and the nucleus, electrons, protons and neutrons, right? So we know that atoms are actually made up of something else, so they're not indivisible, right? And we've actually been able to separate out, right, electrons and protons. So that part of number 1 is not true. Number 2, all atoms of a given element are identical in all their properties. Is that true? Is every carbon atom just like every other carbon atom? That was his point. They're not all the same. Elizabeth is shaking her head vigorously in this direction, not in this direction, but in this direction. That is not true. She's absolutely right. It kind of hurt my neck as vigorously as she was shaking her head. Your neck works better than mine does. So why not, Elizabeth? If she can stop laughing for just a second. Give her a minute, everybody. So how are they not the same? Can you give me an example? Isotopes. Yep, that's exactly right. Isotopes. We now know that, and carbon's a great example of that. If you've heard of like carbon-14, that number 14 there is the number that identifies how many protons and neutrons that carbon atom has combined together. The combined number of protons and neutrons. Carbon-12, however, has a total of 12 protons and neutrons. And actually, the number of protons don't change. What changes with each of them is the number of neutrons, right? So you're exactly right. That was so good. I normally never do this, but I'm going to have to give you an extra point on that one, especially since she was laughing so hard I didn't think she was going to be able to talk. But isotopes, that's what isotopes are, right? So the number of neutrons do vary, and so all atoms of a given element aren't necessarily identical in all their properties. They could have varying numbers of neutrons. Very good. But other than that, this is pretty good, right? Like I said, coming up with this in the early 1800s, that's impressive. And this gave way to the definition of what we call a molecule. And we base that on number 3. Compounds are formed when you combine 2 or more different kinds of atoms. And so let me define a molecule. Molecules are a combination of 2 or more atoms joined together. And so that goes with number 3 in Dalton's atomic theory. H2O, like we've said already, it's a combination of 2 different atoms, hydrogen and oxygen. And then number 4 agrees with how we still define chemical reactions. The atoms that were there initially don't turn into completely new atoms, right? They just rearrange in the chemical reaction. So atoms from one compound may jump to another compound. They separate and then those atoms are rearranged, but you still end up with the same atoms at the end as you started with at the beginning, right? And that makes sense because of the law of mass conservation. Okay, so pretty impressive theory for somebody that long ago, given what we understood scientifically at that time. All right, that's all that I have today. Anybody have any final questions? Got a test? Take it home. I would recommend doing that tomorrow, right, while that material is fresh on your mind, and then jump into the chapter 2 stuff. All right? You guys have a good rest of your week.